All right, finally got my slides started. All right, so sorry for the delay. So yeah, the talk is called "To Spawn or Not to Spawn," Revisited. Revisited because I gave this talk back maybe about 14, 15 months ago at Columbus Elixir when it was over at Rev 1. It's been updated with a few bonus additions as we've actually been doing some really fun stuff with live processes. So that's me. I'm Matt Jones. I work here at Scriptdrop. Yeah, so about this, a quick note about this talk. This talk is summarizing an article that's pretty common to reference, called "To Spawn or Not to Spawn." Highly recommend checking this article out. It goes into a lot of what I talk about here in a lot more detail because, of course, it's text and not speech. And it also includes a full set of working code examples for doing the techniques described. So yeah, processes in Beam. So when we talk about Erlang, the number one thing we talk about is processes. One of the Beam's core distinguishing factors is this idea of you can support thousands, if not millions, of concurrent processes and things like that. Processes in Beam are lightweight. They only communicate by sending each other messages. You can use them to simulate mutable state by essentially just having a process that's responsible for holding a piece of data and updating it when you send it a new value. So the kind of standard example of this is the agent in the Elixir standard library. So if you haven't used it, agent is a tiny little process. You boot it up with start link here in the example. And then once you do that, what it actually returns is it just returns an Erlang PID that says, hey, here's how to contact this agent. And you can tell the agent to update its state. You can tell the agent to get its state. You can do all the things that you normally would have done in some kind of a mutable data structure. And you can pass this PID around almost like a global handle to this data. But underneath the hood, obviously, it's just replacing the state. So agent's kind of handy. Do beware. It's really easy to get into a lot of odd situations. If you tried to build your entire system with nothing but agents, you'd have a very bad time. And an even bigger warning here, because this is a really big trap for the unwary, processes are not objects. So if you're coming from a language like Ruby, like I did, your first inclination is it's like, oh, so I have this little tiny piece of encapsulated mutable state that I can send messages to and get replies back. That sounds a lot like an object. Processes are not objects. If you try to use them like that, you will have a bad time. So just beware. For instance, there are good reasons why you don't want to do that. Processes are fully asynchronous. Imagine if every object in your Ruby code base was executing in its own operating system thread. Yeah, it would be bad. It would create a lot of mysterious synchronization problems where you send a message to somebody and they send a message to somebody and something sometimes happens in one order but sometimes happens in a different order because of reasons, because of the network, because of all sorts of things. Processes can fail. Imagine if every object in your system could just suddenly decide to stop working. It's not really a situation we want to get into. And the biggest one, and the one that bites the unwary unexpectedly the most, processes are not allowed to have communication cycles. So if I'm an Erlang process and I send another Erlang process a blocking message, like with genserver.call, and if that process loops back around and tries to do a genserver.call to me, Erlang will blow both of us up. It's like, I don't know what y'all are trying to do, but it's not going to work. You're going to deadlock, so I'm torching your whole process. Really delightful when you make what looks like an innocuous call and it just blows up your process because it eventually circled back around to the part that you were already executing in. So there's a division here that I think we need to call out between two kinds of concerns when we're designing a system. One of them, this is the article's terminology, so that we're aligned. So the article refers to two kinds of concerns: thought concerns. So those are the ideas that are at the heart of your system. So those are things like deck or round or player. So here we're modeling a card game. So these are abstract entities that actually model our domain. If you have read any of the domain-driven design stuff, this is usually what's referred to as a domain model. And these are specifically called out in contrast to the alternative, which are runtime concerns. So runtime concerns do not necessarily correspond to anything in our model. They correspond to behavior at execution time. So if you say, this thing needs to be fault tolerant, or this thing needs to have jobs executed in parallel, that's not a quality of the data model. It's still the same data, but if you're adding parallelism, that is changing the runtime behavior of the system. So the gist of the article comes down to things that are runtime concerns should be processes. So on the flip side, you've got thought concerns represented by plain old functional programming functions. So functions that operate on data, frequently you group them into modules, all of the usual Elixir ways of structuring things, but all within one thread. This has a lot of nice properties because if it's all in one thread, then your execution is highly predictable. You can be like, it's going to do this, this, and then this. And on the flip side, runtime concerns should be represented by processes. So if you say, hey, I need to have 3 of this running in parallel, there should probably be 3 processes somewhere. So the article works through this long example on Blackjack. I'm going to try to convey the gist of it. So it works with a very simplified set of Blackjack rules. So you start with the first player, you deal them 2 cards. You have your choice of either standing and ending your turn or hitting for another card. If you score over 21, your hand is busted and you are no longer able to play. You ask each player for moves until they are busted or stand, and then you go on to the next one until everyone's played. So this is simplifying some of the rules of Blackjack. There's no concept of a dealer. There's no house rules. There's a whole bunch of other stuff. But the general idea of this is a multiplayer system where people are interacting is still there. So a core thought concern of a card game, obviously, is here is the deck of cards. So in this case, they chose to represent the deck of cards as a list of maps. Depending on your preferences, you might represent this instead as a list of structs. I'm a firm proponent of if you're going to have maps that have fixed atom keys, we have a name for those. They're called structs. Other people may vary. There's only 2 operations that you can actually do to a deck. If you have a fixed set of cards, because notice this is initializing at cards, so it's initializing a compile time module variable to this fixed list of all of the cards that we are using. So if you want to get a shuffled deck, all that is a list of those same cards but in a different order. So there's 2 operations. There's shuffle, which just shuffles the list of cards. And then there is take, and so that says, okay, given a list of cards, pull one of them off and give me back the rest of the list and that card separately, or say, hey, you ran out of cards and return error empty. So pretty common Elixir or even Erlang structure here too, where just basic functions on a data type. There are no processes here. There are no anything. There's just structs and lists in memory. So there isn't really a deck type. It's just a list. Doesn't need anything else. The deck module, if you go and look at the full source code for this article, the deck module collects all the related functions for manipulating decks of cards. And you'll notice if you go back, take here is a pure function. So this being Elixir, you're not allowed to modify the deck. In this case, you really wouldn't want to modify it. But so you not only have to return the card, but you have to return the remaining deck so that you can pass it along to the next step. So yeah, take is a pure function. You feed it a list. If it splits it out, gives you the first element of the list, and the rest of it just does all this stuff. Another big thought concern. So we have Blackjack. So we have cards. You want to put the cards in groups. So each player has what this setup calls a hand. So you say, hey, take all the shuffled cards, take your hand, take some cards, put the cards in your hand. So even if you don't know the definition of these functions under the hood, this process should make a little bit of sense, because again, it's using domain terminology to talk about how we're transforming our input model to reflect the results of the hand. And then there's one last piece. The last thought concern is the round. So the round is the whole state of the game. It is where are all the cards, who's got them, who's busted, all of that. So yeah, player identities, the deck, the current player in their hand, remaining players waiting to move, and who is still in the running. So round is just a plain old in-memory Elixir data structure. Round has two public functions in the implementation in the article. One is start. So start says, hey, give me a list of players, and it will return you a new set of a new round and a list of instructions, which I'll describe here in a second. And then move accepts a player ID and an action. So it's saying, hey, this person said hit, or this person said stay. And it returns an updated round and additional instructions. Or in Erlang code, this is what it looks like in the example. So again, we have none of all of this is defined in other functions here, but hopefully you should see at a high level these names make sense in the domain. So we're saying, okay, if we deal the round, either it's okay or we bust out. And if we bust out, we notify the next player and we skip on to the next hand. So you may have seen a mention in this slide about instructions. So there's a general technique, I think if I remember correctly, it's called defunctionalization, of basically taking where you would have written maybe a callback function, and instead of returning a callback function in certain situations, you instead return what the article would describe as instructions. Other domains may call these different things. If you're in if you've used Redux, there's a similar thing where you make a Redux action and dispatch it. So it's the idea of this is a data structure which represents what needs to be done. So here you might for instance see this tuple where it says notify players in the first element. That's kind of the thing, which player it is and what they should be notified about. So this isn't notifying them. All this is saying is here are the directions. So this pattern has a lot of names. The Haskell wizards will recognize this as a standard monad situation where you're returning instructions which bear a strong resemblance to some of the stuff that goes on in the IO monad and some things. If you don't know what I was talking about, do yourself a favor and maybe don't go too far down that rabbit hole. It is deep and interesting, but it is very, very deep. Elm has a similar thing. If you have written applications in Elm before, every Elm update action returns a list of other commands, they call them, things to do, whether that's updating the view and some other things. You also may see these talked about as events in event sourcing. So if you have something that produces database modifications in an event sourcing model, it's not really modifying the database directly. It's usually spitting out events that say modify the database like this or some other higher level thing on top of that. So the idea of this in general, this whole technique in general, is separate what needs to be done. So that's sending people messages or updating the database or whatever from actually doing the thing. And what that lets you do is that lets you decompose also where those decisions are made. So down in your state code, you can decide which actions to return, but somewhere unrelated, you can say, okay, now given those actions, what should let's actually execute them. So executing instructions is a runtime concern. So because it can vary depending on all kinds of factors. It's not a card, it's not a deck, it's not a round, it's not a player, it's not a domain concept. It's about how we're implementing this into the system. So for instance, notifying players is a perfect example of a runtime concern. It is parallelizable. Everybody, if you have 10 players and you need to notify them all, assuming that you've got enough CPU and network bandwidth, you can totally just run all those in parallel. It could fail, like Slack could be down, players could be misconfigured, all sorts of things could go awry. But again, those are all runtime concerns. So the way that the example does this is with a process tree, because this is the beam. And you'll see this pattern a lot. So we have this idea of there's a Blackjack registry that registers all of the rounds that are being supervised. And here it's using Blackjack round soup, which is a simple one-for-one supervisor. Be warned, simple one-for-one is super deprecated. I think it was deprecated in OTP 18 maybe. So it's been gone for a hot minute. There is now the preferred option in Elixir land is either dynamic supervisor, or if you're running across multiple nodes, probably something like horde supervisor. But the approach is still the same. It's just a question of which piece of plumbing that you use. So each round of Blackjack, so each group of players that are playing at a common table is being represented here as a round server, and then a bunch of player notifiers. So again, rounds are a great example also of a runtime concern. Rounds are independent. If this group of people are playing Blackjack and this group of people are playing Blackjack, there's no synchronization between them in this simple model. There's no waiting, there's no blocking. If this one for some reason, if someone managed to try to put in like the 13 of clubs, one of them might explode, but the other one should be fine. And again, players can be notified in parallel. So lots of stuff happening at runtime, powered around this single-threaded domain. So round server, this is the heart of this whole thing. So a round server represents a single round. It's implemented as an Elixir, as an Erlang gen server. So if you've used gen servers before, by the way, if anyone's looking for a talk, writing your first gen server would be a good talk, hint, hint. So it is a gen server that maintains a round as part of its state. So again, that round is just our in-memory data structure that represents who the players are, where the cards are, all of that sort of thing. Round server is exclusively concerned with taking incoming messages, interacting with the round using them, getting the instructions that come out and executing those instructions. It doesn't know anything about the rules of Blackjack. All of the details of that are delegated down into round. If you're used to doing more OO stuff, you might describe round as your business logic. It's a little blurrier here, but round server, yeah. So if you were feeling really sporty, you could put the state of your round servers into ETS or into Postgres or into some other persistent store, and then they'd survive restarts and fun stuff like that. So the instructions that come out of the game are all about notifying players. So round server is using player notifier under the hood to say, okay, I got this instruction that said notify player 17 that this happened. Here notifier, you do it. So player notifiers are set up as a behavior. So there is a single behavior that all things that can notify players are defined to do. So for instance, you might have one that notifies players over a WebSocket if they're connected via a WebSocket client or a Phoenix channel. You might have another one that notifies AI players and just has the AI play through that interface. You could get real sporty and have one that notifies people via IVR. I don't know why you'd want to play Blackjack via IVR, but somebody probably would. So, like I said, many different ways. At the end of the day, all that happens in all of them is that they just relay messages to the player and deal with retrieving messages coming back. So the nice thing about this architecture, it keeps things organized in a tidy fashion. So if you change the game rules, you are probably touching round and player and card and things like that. These core data structures that are your domain model. On the other hand, if you wanted to add something where it says if you don't play within 5 minutes, we say that you busted out and kick you out of the game. That's something that probably lives in a player notifier. And again, changing the way that if you want to change the way that players' moves are input, we already talked about that a little bit. You would supply a different module that behaves like player notifier. So that is the gist of the old part of the talk. Now we're getting into the new part. So I'm going to walk through a couple of quick real-world examples based on some code that we are actually using here in production at Scriptdrop. So my first little example of a runtime concern. So we encountered a problem. Erlang really likes to restart things. Like really likes to restart things. So if you have a process which crashes every time it boots, the beam will restart it over and over again, and if you restart it too often, it will start blowing up more supervisors because it thinks it needs to blow more stuff up so it can restart all the things. Yeah, that's not good. So it turns out if the old mantra is let it crash, I think that should probably be amended to let it crash if crashing will help, because it turns out if you've got code that every time it gets to this spot it always crashes, restarting it just makes it crash again. It's not really helping. So we had this issue where restarts would just keep going. It would consume system resources. It would blow up on unrelated parts of the system. It was really bad. So we added a piece of logic to our live processes using what we're calling restart limiter. So restart limiter is a tiny little gen server. Its only responsibility is to decide whether or not this process should start now or in about 30 seconds, or not at all if it's restarted too many times. So workers show up, they say, hey, I'm this worker, they give a name, restart limiter decides how to respond. If it's never seen that name before, it just replies back with okay. It's like, yep, keep on restarting, it's awesome. If it's seen that name before and within a predetermined time window, it says, hold on there, cowboy, and literally just sleeps for, I think it's 20 seconds. And then tells it, okay, you can try booting up again to reduce the thundering herd effect. And if it's seen that too many restarts in too small of an amount of time, it just says, nah, don't even bother. You're done here. And it tells the process, and the process is responsible for saying, okay, I'm actually done here and stopping. It logs something it logs out and says, hey, we were abandoning restarts for this one because it's broken. So the actual implementation of this is a little bigger than will fit on a slide. I think I have a piece later on which it's 103 lines of code total in the file, but that counts everything from def modules, that counts function heads, that counts the bare end at the end of functions, that counts the blank lines. So it's probably more like 70 lines of actual code. But putting 70 lines up on that screen is going to make something that nobody can read. So I broke out two of the relevant pieces of this code. So this first one, so if you've not dug around in GenServer, this won't make a darn bit of sense, so I'll give you some background. So GenServer expects some callbacks. In particular, two of them are handle call and handle info. They're related to particular ways you can send messages to the GenServer. So when a process in our system starts up, or when the relevant processes in our system start up, they send restart limiter this check restart message. Along with their name, and so they're basically saying, "Hey, should I start?" And so then restart limiter says, "Okay, if we should do a prompt restart, just reply back with an okay, and we're all good. Otherwise, wait a restart delay, and send ourselves a message that says, okay, now it's okay to reply." And that handler is there. So this is a kind of a cool thing. In some languages, this would be real nasty. In Erlang and Elixir, it doesn't really look like much. But you'll notice here, handle call. The second argument to handle call is a tuple called from, and it describes the caller. So it's an opaque reference and a PID for the caller. So the beautiful thing is the caller for this first function, check restart, the caller is blocking, waiting for this to reply. So you'll notice if we aren't supposed to boot the process promptly, we don't send a reply. We reply to GenServer with no reply, which just says, just go back to executing. Don't reply back to the caller. And so we reply later. So we take that from tuple that we got in the first function call, and then we just we stashed it in our state, and then we spit it back out later. It's pretty slick. So you may notice there wasn't any explicit data manipulation in here. Everything was in named private functions. That's a nice bonus of this style. But like I said, real short file. It does one thing. It either sends you back an okay right away, an okay in about 20 seconds, or an error. Tiny little file, super handy. And it's one of the things that I've really started to enjoy about the Beam is building, like, if you were really into microservices, you might be able to close your eyes and pretend that this could be a microservice, but it's almost too micro for that. Like, it's too small for a microservice, but it's perfect for an Erlang process. So yeah, total implementation, 103 lines of code, including blanks and trailing ends. and it encapsulates really nicely a single runtime concern. So a more complicated example. So here at Scriptdrop, we have integrated with a bunch of different ride-sharing platforms because it turns out sourcing couriers is one of our biggest challenges. And these platforms have lots of people who are interested in delivering things from A to B and can be summoned via API. So it's kind of awesome. So the way that those platforms work is they receive a request, they dispatch a driver, and for the most part, their drivers don't interact with our system directly. Their drivers continue to interact with the ride-sharing company's application, but they send us the ride-sharing company sends us webhooks. So it says, hey, the driver has arrived at the pharmacy. Hey, the driver has picked up the thing. Hey, they've dropped it off. Like all of these kind of pieces of information. So our system responds to these incoming webhooks by updating our internal order status and things. And that would be fine. Like you could write a system in almost any language that would do that very smoothly. Like you could, I certainly wrote a few of those in my day in Rails where it's like, hey, get a webhook event, figure out what record to touch the record, everything's cool. The problem we have is we also need to be able to do things when we don't get webhooks. So we need to be able to say, okay, this driver accepted this delivery. If they don't show up in half an hour, start ringing people's phones because that means something has gone wrong or we've lost a webhook or more likely we've lost a driver or something like that. And that's hard to do in traditional languages because it's one thing if you're saying, okay, in response to a webhook, we're going to do X, Y, and Z. That's awesome. But in response to not seeing anything for X amount of time is trickier to do. If you were in a more traditional stack, you might resort to background jobs or something where it's like, okay, well, if I don't get an event, if I set a background job to go off in 20 minutes, but if I get an event, cancel it, and you end up with these weird race conditions, and it's very bad. So under the hood, how we do it is with a very similar system to what I described with Round Server and its associated components. So we have a registry that is responsible for mapping names of these instances to their PIDs. We have a supervisor that's managing one process per live delivery. And then each delivery that's out there in the wild going on is represented by a different tracker process. So we have a couple of different ride-sharing platforms we integrate with. So we have several different flavors of tracker processes because they all speak very slightly different dialects in terms of what they do with webhooks and all kinds of fun stuff. So each one of these tracker processes is built on top of a great little library. It's part of the Erlang standard library. So if you're running Elixir, you already have this code on your machine. You may not be as familiar with it because it's in Erlang, but it's really out there. So each of these trackers is built on a package in Erlang called genstatem, actually wrapped here by a package for Elixir called genStateMachine. But if you read the docs for genStateMachine, about 85% of them are, here's a link to the docs for genstatem. Hope you know Erlang. And so genstatem provides us with a lot of useful abstractions. In particular, the one that we use the most is called a state timeout. So it encapsulates this very common pattern of, okay, I'm going to set a timeout. If my state machine hasn't changed state in the next 20 minutes, send me an alert, send me this message that says that I hit the timeout. So genstatem under the hood is automatically taken care of. Okay, if I get another message and I change my state, then that timeout's going to be canceled. So it's not like I've written some really horrifying JavaScript where it's like, oh, well, if you set a timer, you've got to make sure to cancel it, otherwise it fires in weird places later. It turns out I'm pretty sure that the authors of genstatem had hit that problem before, and they were like, you know what we're going to do? Make that not be a thing we have to deal with. So yeah, state timeouts are really slick. So this example is not going to make a huge amount of sense because it's double whammy. It's domain specific to our domain, which is not going to make a ton of sense. And it's genstatem specific, so it's going to make even less. But I'll try to walk through it. So genstatem defines you essentially define a function a function head for each state that your state machine can be in. So here, one of our state machine states is called requesting, and then those heads take different arguments depending on what is happening to your state machine. So in this case, we are seeing when we get an info message with this payload that says ride requested and has a tuple of OK and an actual payload in it. And just like we saw with some of the round server stuff, genstatem is going to return tuples. So this tuple that we're returning to genstatem is saying, all right, here's the next state. So you can return a bunch of different possibilities from a genstatem callback like this. You can return keep state in data, which is just saying everything's cool. Don't worry about that message. We got this. You can just say keep state and return new data. You can say next state and return new stuff. So here in this case, we're saying, okay, if we're in requesting and we get a payload back from the ride requested endpoint, that means we have successfully been assigned a ride. So what we should do is now go to where we're waiting for a driver to be assigned to that ride. So we're saying in the next state is assigning. We update our data to include this piece of the payload. Here it's the ride ID because when the rideshare companies contact us with a webhook payload, they are not telling us here's a webhook for Scriptdrop order 1234. They're telling us here's a webhook for rideshare company or rideshare company ride number ABCD. So we keep that mapping headed up. And then there's one last little piece here where these functions persist action and register external action. So persist action just returns a tuple. It's down here at the bottom of the slide. And the way that this works is genstatem is doing something very similar to what we saw at the very beginning with instructions. Because under the hood, persist action, so again, persist action just returns a tuple. So persist action is a function that makes an instruction for genstatem to subsequently execute. So genstatem is almost embodying part of this pattern already. So again, if you've used dispatched actions in Redux or some of these other things, you'll see this pattern. So yeah, we're right back to instructions again. So some further reading. Again, please highly recommend checking out this article. I will post the URL to it in the Columbus Elixir Slack so people can check it out. Other good things to read. There's a big chunk of functional web development with Elixir, OTP, and Phoenix. It's one of the prog books. Highly recommended. It is not primarily about the data layer part of Phoenix, so I don't think they get to Ecto until the end, if at all. But it is about the idea of, okay, first build your data structures in a way that makes sense in memory, and then figure out how to attach that to the web, and then figure out how to make that persistent. So I don't know if it's always the right design approach, but it's definitely an interesting one and a very Erlang and Elixir specific approach. So highly recommend that read. And then another classic, if you've seen it, I believe this is either a JavaScript or a Ruby talk, but Functional Core Imperative Shell by Destroy All Software. Has, again, it's a very similar idea where it's like, okay, in the heart of your system, you have this domain model, which is ideally built using functional languages and nice immutable data structures, very easy to reason about, very easy to unit test. And then around that, you have this imperative shell where it's like, okay, I need to be like, okay, first you need to do this, then you need to do this, then you need to send that thing an email, then like, this is not a side effect free operation. Like, this is only side effects. That's all I care about. So again, a good read to kind of get used to some of this stuff. And that's it for me. So, questions?